We left off talking about metals, right? Various kinds of metals used in construction. They could be in the columns, beams, or joists. In steel construction, they could be metal studs if we happen to be framing with metal studs rather than wood studs. We obviously can have metals in windows and doors. Aluminum, it would be a common metal that's used in windows and doors. We can have standing seam metal roofing, excuse me, metal gutters and downspouts. Metal in the plumbing systems, obviously the copper in the electrical system, hardware on doors, et cetera, et cetera. Sorry, so lots of places that metals are used in construction. We watched this video here. Again, inexplicably, they had the little thing of that guy barking on his cell phone. So why that was in the middle of it, I don't know. Metals generally classified between ferrous metals and non-ferrous metals. So ferrous metals contain iron. They have magnetic properties, and iron and steel are both ferrous metals. And iron can be cast iron or wrought iron. We'll see in a minute how steel is made. Steel is a combination of iron with a little bit of carbon and some other components in it. Non-ferrous metals do not contain iron. They're not magnetic. Some examples of non-ferrous metals: aluminum. Right, we just talked about aluminum in windows and doors, copper in plumbing and electric wires, brass or bronze. Sometimes brass is used in plumbing fixtures. Bronze might be door hardware, et cetera, et cetera. The surfaces of metals are often treated to provide a certain look or finish. Again, just like bumpers on 1950s and 1960s cars were chromed to make them nice and shiny, we can chrome a metal to give it a shiny surface. We can galvanize steel. It's a coating of zinc to provide rust resistance. Again, we used to quite often use galvanized piping in plumbing systems. We don't use it as much anymore. We'll talk about plumbing here a couple weeks out. We can have a protective layer on rust on certain kinds of steel. That's called Corten, C-O-R-T-E-N steel. And again, I use the example of the Daily Center downtown that has Corten steel. And we can electroplate. We can adhere some kind of metallic coating on the surface to provide a thin, in essence, a veneer. Thicknesses, as it says here, metals less than 1/4 of an inch in thickness are classified by a gauge system, right? So gauge will talk about the thickness of the metal. So you might see a specification that says something rather shall be made of 14 gauge steel or 14 gauge aluminum, right? That gauge, G-A-G-E, refers to the thickness. Okay, so we're going to watch a video on steel production. So let me swap that around. Hold on.
Few fireworks displays are more spectacular than the drama that is steelmaking. The story of hot metal and cold steel is fascinating from start to finish, especially when seen through the experienced eyes of United States Steel. For our company, the story begins with a blast. As rock explodes and the raw materials of steel are tossed from the earth. The rock is taconite, and the prize inside is crude iron ore. We get at it by grinding the rock to powder and separating the ore with powerful magnets. Then we form and heat the ore into marble-sized pellets that will later be converted to iron. From bituminous coal, we create coke to fuel the iron-making furnaces. We crush the coal, seal it in airtight ovens, bake for 12 to 16 hours, and remove it from the oven as solid carbon fuel. The fuel and pellets come together in the blast furnace, where we add just enough limestone to remove impurities. From below, a continuous blast of superheated air combusts the coke, intensifying the heat and changing raw materials into molten iron. Sometimes more than 9,000 tons of it a day in our largest blast furnace, where it reaches a temperature of 2,700 degrees Fahrenheit. At regular intervals, we tap this blistering brew into giant submarine ladles that ride on rails to the basic oxygen shaft, where iron will be turned into steel. In this fast-paced sequence, up to 250 tons of steel can be made to order in less than 45 minutes. We begin the steel-making process by dumping recycled steel scrap into the basic oxygen furnace and adding hot iron. Sparks steal the show when high-purity oxygen is blown into the mix at supersonic speeds and molten iron becomes molten steel. Now we're ready to create the custom blends that make steel the most widely used metal on the planet. In fact, we produce over 1,500 different chemistries to meet customer demand for cutting-edge, value-added steel. Look for another show of sparks as we tap molten steel from the Bach vessel into a ladle. Then, for most of our steels, it's on to the vacuum degasser, where they are made highly formable. The focus then shifts to forming and finishing, which determine even more of the steel's characteristics. The first step in this sequence is to position the ladle above a massive tundish or funnel that feeds a continuous caster containing molds that shape the steel. The molten steel, now at 3,000 degrees Fahrenheit, is channeled from ladle to tundish to caster, where it cools to a red-hot solid. The shape of the mold determines the shape of the semi-finished products that come out of the caster. And since most U.S. steel plants make sheet products, most of our casters output slabs, typically 8 to 9 inches thick and 3 to 5 feet wide. As they exit the caster, slabs are cut into sections up to 40 feet long and stacked to await further processing. Then it's on to the hot strip mill. This is where we begin transforming steel slab into steel sheet. Slabs are reheated to 2,400 degrees Fahrenheit and descaled before running through a series of roughing stands that make them thinner and longer. Then they cycle through finishing stands where they are rolled even thinner. Finally, they are cooled and rolled into coils that may be thousands of feet long but only fractions of an inch thick. A far cry from the chunky rectangle that came out of the caster. And the entire process is untouched by human hands, controlled instead by operators using state-of-the-art automated equipment in pulpits that overlook the action. Next, we move to the pickle line, where coils move through an acid bath that cleans the surface. Some of the emerging coils are shipped directly to customers as hot band. Others are destined for applications that require special finishing, beginning with cold rolling to make them even thinner. At that point, coils may be shipped or go on to one or more additional finishing processes. Coating to make the steel resistant to corrosion. Tinning to further reduce the gauge and add the tin coat we commonly see on canned goods. Annealing to make steel that is easier to bend and form. And tempering that uses special rollers to add hardness and create surface textures and other special finishes. In fact, many of our products leave the finishing facilities as the industry's newest superstars. Lighter, stronger, highly engineered, formable steels that were unheard of just a few short years ago. No wonder the story of steelmaking stays so fresh, with innovations that guarantee something new to see in each showing, with product placements in our homes and high-rises, on our highways, and in every other part of our daily lives. And with a cast of thousands who continue to improve and perfect every step of the steel-making process, from shaped pellet to shipped coil and beyond.
Okay, I found that interesting. Back to where we are here. Yeah, so that's luckily no advertisement, because the advertisement is U.S. Steel. You saw a couple places it said Gary Works. Obviously, that's the large steel plant along the lake in Gary, Indiana. So that gives you some sense of how steel is made. I think one of the important things there is that steel can be recycled. Right, you saw where they charged scrap into the blast furnace. Right, so we essentially can take apart old buildings, take apart old things, and melt that steel down and turn it into something new. So, you know, that's a characteristic of steel, is that it's you know, in essence, it's infinitely recyclable. Right, we can melt it down and make new steel. Okay, so that was steel production. If we have time, I have another video about how they made steel in World War II era. We'll come back and watch this again if time allows here, but it's another 9 minutes or so, so I have to watch the clock and be careful, but it'll be interesting when we see what they did in 1944 versus what they're doing in that more recent video. Okay, so structural steel is a term we applied to hot rolled steel sections of various shapes. So again, all those different shapes will be produced, you know, from an ingot and rolled into the various shapes that we saw. A lot of what we saw in the video was sheet steel, but the same techniques will apply to the other shapes that we see in construction. Right? We often see structural steel of this shape, right? A W or S section. You see the term web and flange. I happen to stick a picture in there of a steel I-beam that you might see in residential construction, right, holding up the wood frame above it. So again, these are called I-beams, right, a web and a flange. You know, certain designations for how we describe those different structural steel shapes, so that, right, that W shape I-beam would be described one way as W12 by 16. So W12 means a 12-inch beam that weighs 16 pounds per linear foot. So in the drawings or specifications, you might see W12 by 16 called out. Angle is also described. Here's an L 3 by 3 by ½ inch, right? 3-inch long legs that are ½ inch thick. And this is in the book. Let me find out exactly where it is for those of you who are following along. Sorry, I got myself sidetracked here. So this table is on page, this is figure 7-19 on page 121, right? Different shapes, its descriptive name, a view of the shape, the letter that identifies it, and a designation. Again, depth and weight. So S8 by 23, 8-inch deep S shape, 23 pounds a foot. Again, here's the bottom half of that same table. So again, lots and lots of different varieties of steel that can be used in construction. Okay, let's switch to Division 6, which is wood, plastic, and composites. I think we'll see a number of pictures here. I mean, here's a good picture of low-rise construction that's wood framed. I think somebody asked last week about, how much we do residential construction in CMU versus wood. We do a lot of stuff in wood for a variety of reasons. Number one, wood has got, good strength both in compression and tension. And we talked about that in relation to concrete. Concrete was good in compression, squeezing it together, but not very good in tension. Wood has good strength both in compression and tension. We can use wood for structural framing, rough carpentry, and also for trim and floors and walls and cabinetry. It's called finish carpentry. And we generally classify woods as either hardwood or softwood. Where do those classifications come from? Well, they come from the type of tree that the wood is obtained from, right? Generally speaking, we can group trees into two categories, coniferous and deciduous. So coniferous think of them as pine trees, small needle-like leaves. Generally speaking, the needles stay on the tree, as opposed to a deciduous tree, broader flat leaves where the tree loses its leaves in the wintertime. So coniferous tree, doing the order here. Hard deciduous trees are generally hardwoods, right? It says in the little thing there, hardwoods come from deciduous trees. Right, hardwoods are typically used in furniture, flooring, trim, and veneers. So oak is a hardwood, maple, ash, teak. Right, we don't frame houses with oak or maple because it's too expensive and the wood is hard and difficult to work with. Some of these images are not in the book. I'm generally in page 122 of the book, but I've added some additional materials in this lecture to better describe what we're talking about here. Softwoods, again, from coniferous trees. So pine is a softwood, spruce, cedar, fir, Douglas fir, those are all softwoods, right? Most of the timber that we use, most of the wood we use in construction are softwoods. They're faster growing than hardwood, and they still can be quite strong. So we're typically going to frame or use softwoods, use pine for the framing, for the rough framing in a building. Right, here's This is, that little table is on page 122 of the book. Again, some examples of hardwoods and softwoods. Right, cherry is a hardwood. You make beautiful furniture out of cherry or mahogany. Flooring in maple or oak. Right, again, I live in an older house, so I have maple floors in the kitchen and oak floors in the rest of the house. I have oak trim. You know, lots of beautiful detailing that doesn't necessarily get put in houses anymore because it's too expensive. Right, lumber is classified as either rough sawn or surfaced or finished size. So rough sawn would mean it's cut to rough size, but it's not dressed or finished, dressed or surfaced. Surfacing means that we've run it through a planer to its finished side. And you see the designations there about being finished on 2 sides or on 4 sides. We always, in the right, dimensional lumber means it's lumber that's cut to a specific size. And we always have to distinguish between the nominal dimension and the finished or dressed size of the lumber. And if you notice here, it says nominal dimensions are always written without inch marks, right? So a 2 by 4, those are the nominal dimensions of a 2 by 4. We'll see in a minute what the actual size of a 2 by 4 is, right? So the dressed size is the dimension of the lumber after it's been seasoned and finished, right? The dressed size is less than the nominal dimensions. And the other important thing here, it says the dressed size is always written with an inch mark. So, right, sorry, this one's a little fuzzy here. So a 2 by 4 is a nominal size, but the actual dressed dimension of a 2 by 4 is 3.5 inches by 1.5 inches, right? Same for a 2 by 6 or a 2 by 8, right? So a good trick question that somebody might ask you is, how big is a 2 by 6? And if you put, oh, it's 2 by 6, well, you're not distinguishing between the nominal dimension and the dressed dimension. So again, the nominal dimension doesn't have inch marks. The finished or the dressed dimension does. Right, here's an example of rough lumber being used in rough framing to frame a house. In this case, it's a stick-built house. Stick-built is the term that's applied. We sometimes will think of a piece of lumber as a stick. Stick building generally means that carpenters are building the house with individual sticks on site. And I distinguish that, and I probably should have put the slide in there, distinguishing stick built from modular. You know, we can modularize some construction. We can build sections or components of a house in a factory and ship out pieces to the job site. I think we should be doing more of that. We don't. We do a lot of stuff as stick built, right? So a bunch of carpenters cut pieces of lumber and they nail it together and they create a structure out of it. In stick building, there are generally two framing types. The older style of framing is called balloon framing, and more typical construction style today, framing style, is platform framing. It's a little hard to see here, but the main distinguishing characteristic of a balloon frame is that vertical member is one long piece of wood. In this case, that comprises 2 stories high. And then at the floor, this floor joist is in essence hanging off that stud, as opposed to a platform frame house where each floor is framed individually. So we used to build houses using balloon frame construction. So probably a lot of the wood construction in the older wood construction in Chicago is balloon frame. Why did we get away from balloon frame construction? Well, 2 reasons. Number one, it's hard to find a nice piece of wood that's 12, 16. Let's say it's got to be 20 feet long, right? If we're framing a 2-story house with 9-foot ceilings, you might need a piece of lumber that's 20 feet long, right? There just aren't that many good trees anymore that produce a straight stick of lumber of that length. The other thing has to do with the fire resistance of the construction. In this case, in the event of a fire, that flame and smoke can kind of jump right up between the floors, in that channel where we blocked it off in platform frame construction. So right, again, here's an example of balloon frame construction. And let me show a little video here. Hold on. Right, so that's balloon frame construction. Again, that's how we used to build houses. Actually, while I'm here, let me play one more video.
The structural framework of today's buildings can be comprised of many different types of materials. And as you can probably imagine, each one of those materials comes along with it its own unique assembly process. So being able to understand those 2 elements of a structural building system are critical in evaluating a project and determining what is the most appropriate material and method application for that given project. With this in mind, we're going to take a look at platform framing and some of the characteristics of this type of assembly process. So platform framing is the most popular method of light frame construction, primarily used in the residential construction industry, but not completely. So what we should really understand right from the beginning, platform framing operates off of a very simple building block concept. One block stacked on top of the other, supporting the blocks above it. So you can imagine how this type of system makes the method rather adaptable to different building types, particularly multi-level and single-story structures. So if we pull the skin away from these so-called building blocks, what do we find under that? Well, what we see is that each one of those building blocks has a set of support walls and a base to help support those walls. So very basic in nature, but let's dive into that even more and look at what that actually looks like and how it comes together. So let's start with the base or the platform. And if you didn't pick that up, yes, that's where the name platform framing comes from, because of this simple platform idea, building one on top of the other. So the platform is going to start with what's called a rim joist that you see here, and that creates the exterior envelope of the platform. Now within that is going to be the support system for the surface. And the support system is going to be comprised of two basic members, the girder beam, which you see here, and then intermediate joists that are going to be supported by the girder beam and also the perimeter foundation wall, which was already in when we started. Once that is all in place, that provides the support structure to put the surface on, which is going to be our decking. And the decking is going to be made up of 4-foot by 8-foot sheets of plywood, typically ranging anywhere from a 1/2 inch to 3/4 of an inch in thickness. And the thickness of that plywood is going to vary depending on the spacing on your floor joist. And your spacing would typically be 16 inches or 24 inches on center. So once we have our platform in place, now the framing contractor has a good surface to work from to start building those support walls that we talked about. Those support walls are going to be comprised of 3 basic elements: a bottom plate and a top plate, which you see here, and those are going to create the horizontal extents of the wall system. Within the confines of the bottom plate and the top plate are going to go what's called the studs that you see here, and the studs are going to be fastened to the bottom plate and top plate, typically using nails. The studs will create the vertical support and also the vertical limits of the wall height. Now, these walls are going to be load bearing. So as you can imagine, when you start to put a load on the top of those walls, the studs are going to want to react to that load. So horizontal bridging is put in between the stud spaces to create a better load support for the wall system. So once the wall is all framed up, then it will be lifted into place and temporarily supported until the rest of the framework can be put in place. Now, when they put the wall in place, they are going to have to plumb it to make sure that it's standing perfectly vertical. They put their their temporary supports in place, and then begin building the rest of the walls. Now, what you're going to notice here is that the wall, they did not build the entire wall all in one piece. We have 2 different elements here. The reason for that is because, as you can imagine, the larger section of wall you build, the heavier it gets, consequently making it harder to manage when putting it in place. So they build it in segments, making it easier, more manageable in the installation. And the way those wall segments are tied together is with a second top plate, which you see here, that overlaps one wall from the other and gets tied together. So now you've got multiple wall segments within one run of wall that are built separately, put together, and then tied together with a top plate. And that process is going to be continuous all the way around the building perimeter, and then also on the interior of the building envelope as well. And that is the basic setup for giving you your box, your building block that we talked about earlier. You've got your base or your platform, and then your support walls on top of that platform. And if you have a multi-story structure, then the process is repeated for the second level until you get up to the roof level, where the roof is framed up, and that will be talked about in a later video. Now the walls can either be sheathed after they're all permanently in place or while you're framing them on the platform. There's advantages and disadvantages to both, and I'll leave that for you to think about on your own.
Okay, so that was platform framing. Let me get rid of that. And where did we go here? Oops, sorry. Right, so that distinguishes the two main characteristics of, or two main techniques for frame construction: balloon frame or platform frame. Again, balloon frame was how we built houses, let's say 100 years ago. Platform framing are the technique that's generally used today. And let me go back to my slides here. Again, I wish the system gave me an easy way of switching back and forth, but it doesn't. Right, so again, just to review: nominal dimension and finished or dressed dimension or dressed size. Dressed size is less than the nominal size. Nominal size doesn't have inch marks. The dressed size or the finished size does. So 2x4 is 3.5 by 1.5. So less size, smaller than the nominal 2x4. We talked about platform framing versus balloon framing. Right, again, here's some of the characteristics of the platform frame. And this was our video. I have it up on Blackboard already. I think I'm under week 3 now. A Word doc where you can go back and watch these videos if you're so inclined. In the video, they talked about plywood. Plywood is layered, right? The guy said they built the platform out of sheets of 4x8 plywood. So plywood is made of several layers with the grains at right angles to each other. Odd number of layers, so the grains on the front and back are running in the same direction. And thicknesses from 1/8 inch to 1 inch or more. Right, here's a picture of the edge or the side of plywood. Right, you can see the different layers if you look carefully at the edge. Right, another type of lumber is called glue laminated timber or glulam. Right, so in this case, we're taking multiple layers of lumber, bonding them together, and making bigger members, right? Using them to make beams or arches. And this is typically done at a factory, right? We're not going to do glue laminating in the field. We'll buy it from a factory. So here's some examples of glue laminated lumber. You see structural members here that are deeper than what would be obtained just by dimensional lumber. You know, with that additional depth in the framing member, we can have a longer span. Yes, it would be hard to do yourself. I mean, you theoretically could, but again, you're going to buy that glue lam. You know, that'll be, I think of these as engineered wood products, right? Now, you actually use the term on my next slide here, right? Here's another example of engineered lumber, right? OSB is another sheet product, you know, just like plywood. Yes, I believe that LVR's, let's take a look. That's a good question, Vaughn. And me see if my next slide answers that. I think LVLs typically look something like this. So it's not glue laminated, it's typically put together with OSB and made to look kind of like a steel I-beam, but now we have a wooden I-beam. But I will look that up for you, Vaughn. Make sure that I know what an LVL is. I think there's a couple different acronyms there, which I will, I'll go and get the answer for, I think. Yes. Right, so the advantages of some of these types of engineered lumber is that we can have, you know, the same strength with less material than we would with a piece of dimensional lumber, or we can have the same strength and that OSB might be made from, you know, small pieces of wood or flakes or waste from the milling process. A couple places that plastic can be used. I'm not sure of plastic countertops. In fact, I'm kind of old school here. I don't like to see that much plastic in houses, but it's kind of creeping in there. Patrick, I would say that's a good question. These, yeah, maybe they would, right? We again in the city of Chicago, we have lots of buildings that were built with heavy timber, you know, 4x4s or 4x8s. You know, a lot of the you know, mill buildings in the west side, that's heavy lumber, you know, heavy timber construction. That heavy timber is very slow to burn. This stuff here, I don't know. That's a good question. I mean, in many parts of the building, the wood will be covered with drywall, right? Drywall provides additional fire resistance. But in the case of our floor joists, in the case of our floor joists in the basement, they might be exposed. Yes, I think these wooden I-beams would be used typically for floor joists or ceiling. Right, again, we're looking to you know, span a longer dimension. So as we have a longer span, we either have to, you know, have them spaced closer together or have bigger members, right? 2x8s or 2x10s or 2x12s, right? The wooden I-beams allow us to have that same span with less material. Okay, getting back to plastic, I think that probably the most common place we'll find plastic would be in the plumbing systems, which we'll talk about in a few weeks. Okay, let's switch to Division 7. And actually in the book they didn't talk about Division 7, but I had some slides built with especially with insulation, so I had to make up Division 7 because that's the CSI division that incorporates these components of a building. Right, so what do we use insulation for? Insulation is used to reduce the transmission of heat. It's used to, in this kind of weather, right? In my house, I've got the boiler going, trying to keep my house warm so I don't get chilled like I did at the beginning of the lecture. And I have insulation in my walls that's preventing or slowing down the heat that's in my house from leaving my house and going to the outdoors, right? Because heat moves from an area of higher temperature to lower temperature. So the heat that I just spent money to put in my house, I want to keep in my house, and I don't want to heat the outer doors. The term R value indicates how much that insulation resists heat transfer. In the case of an R value, a larger number, a bigger number indicates a better resistance to heat transfer, right? So you have R11 or R19 or R30, right? And R30 insulation is better at reducing heat flow than R11 or R13. And we can classify insulation materials as flexible, blankets or bats, loose fill or blown in various type of rigid board insulation, as we shall see. Right, so again, in our context of building construction, R value is a measure of how well that component of the building resists the conductive flow of heat. So again, in the wintertime, heat's going to flow from the warm inside to the cold outside. In the summertime, direction is reversed, right? So you want the insulation to prevent the hot outside from warming up the inside of your house. Right, and R value is a measure of the insulating value. Right, how much R value you need depends on your climate. It's going to depend on the building code. Again, nowadays, R values are going to be, or minimum R values are going to be stipulated in the building code. Remember, we talked about the building code sets minimum standards for construction. So the building code, either the IRC, the International Residential Code, or maybe the IECC, International Energy Conservation Code. Remember those I codes from a couple weeks ago, those model codes. Those will stipulate the amount of insulation or the R value of the insulation that you need in the walls or roof. Other construction products are rated in U value. So windows and doors are typically rated in U value, and U is the inverse of R. So in the case of R values, bigger is better. In the case of U values, smaller is better, right? We're Americans, so we can generally understand bigger being better. That's the way we think. We just have to remember that R value, bigger is better, U value, smaller is better, right? So if we see a U value for a window of 0.03 or something like that, then we know that that's a good high quality window. So in the I codes, in the IRC or the ICC, the requirements for insulation will vary depending on the part of the country you're in, right? From subtropical Miami up to frigid Duluth, right? The requirements for insulation and for window performance are going to vary in the building codes. So why do we insulate? Obviously, today's a good day to think about why we insulate, right? We want to keep ourselves comfortable in our houses and not have to pay a fortune to heat our house. In the summertime, again, we want to keep ourselves comfortable, not have to pay a fortune to air condition our houses. Right? Another view of the same thing. We're going to essentially provide a thermal boundary between the inside and the outside. We're going to wrap ourselves in a continuous barrier of insulation between the inside and the outside. And again, you can see here, depending on the details of the construction, it would indicate where the insulation goes. So here's our bat insulation, right? This is a flexible product. You see the R19 on it, the R value. 2x6. So R19 is generally for a 2x6 wall. And then you also have to look at what's the width. It's probably 2x6. We're generally going to be at 24 inches on center. The other thing about it says faced. So on this insulation there is a paper backing or facing, right? So this would be a craft faced insulation. Let's actually stop right here. I'm starting to lose my voice and I need a hot tea or a drink of water. So any questions, folks? Vaughn asked a couple of questions about LVLs, which I will have to find the answer to. So why don't we take a 10-minute break? So we will start again at 5 minutes after the hour, give or take. Yes, I'll get back to that, Jose. Good question. Let me come back to that. Both good questions. Yeah, Jose, hold those thoughts, and I will answer. I saw your what's in the chat. We'll have to take a look at that, Patrick. Is it differences in construction or differences? Okay, I will take a look.